suppose the charge Q1 is uniformly distributed over a spherical region up to a radius r equals a. Does that mean like everything inside that sphere is like all like charged?
So yeah, if there's that, so if the charge is uniformly distributed up to a radius, up to a certain point, it means the charge is all throughout. It's all throughout it, yeah.
That was what I was confused. I originally had it so it wasn't like that.
Ah, no, yeah, that's what it means. Other questions? I'll begin with a prayer. So, Heavenly Father, we thank you for this time we have to meet and study your creation. Just pray you help us to solve some of these problems, to understand a little bit more. In your name I pray, Lord Jesus. Amen. As I said, any guess if I can actually solve a problem right now, but I'll let you guys solve it instead. How about that? Let's see, where were we? I was chipping away at chapter 21. I'm going to skip ahead to chapter 22 and do something over there for a change of pace. Let's see here. So somewhere I printed out my list of problems. I'll make sure I'm trying to work the problems on my list, you know. All right, so, which is not to say that the other problems aren't good. I mean, there's 80 problems in the back of the chapters, and a lot of them are good. Let's see here. I've already worked. Oh man, I didn't write down which ones I worked on this announcement. That's a bummer. We'll figure it out though. Let's go to the last one, maybe 2249. I haven't done that one yet. Yeah, I don't think I've done that one yet. That one's got calculus. It's got two blue dots. It should be sufficiently evil to get us started. All right, so it says here, a very long insulating cylinder has radius r, carries positive charge distributed throughout its volume. Notice not uniform this time. And the charge distribution has a cylindrical symmetry, but it varies with the perpendicular distance from the axis of the cylinder. And the volume charge density rho is equal to alpha times 1 minus little r over big R. I think the radius of the cylinder here is r, yeah. So we've got a cylinder. I'll draw a picture like this. So here's the cylinder dead on, and r is the distance. So like this distance is r, right? All right. So alpha is a constant, and we're supposed to derive an expression in terms of alpha and r for the electric field as a function of little r. Do this for r less than r, and also do this for r greater than r, and do your results agree for r equal to r? R. Okay, great. So this is a very long, so basically this is a kind of a twisted version of like the line charge problem. This is 2249. So if I draw a picture of it more like this is kind of like how I've drawn these before, right? And it goes on and on. All right, so this is just I can't draw an infinitely long cylinder, so I just have to be content with this much. And so if that's how the charge is distributed, what direction does the electric field go? Right, so if I draw it over here, the electric field has to be like this way, right? Like, not to say that it starts just at the origin. I'm just saying like these are the direction, right? It's just radially. It has to be like this, right? It can't be along the axis. It has to be perpendicular, right? So the electric field is going up there. It's going down here, and it's coming out at us and going into the board. All right, so now do we agree on the direction? Like that's the kind of the first thing with a Gauss law problem, is to get some kind of mental picture of where the electric field should go. And that will suggest to us where we should draw our Gaussian surface. What do you guys think I should do for this one? Gaussian sphere, Gaussian cube, Gaussian cone? I never did one of those, did we?
I drew a Gaussian cone and he was like, that's not fun.
Tell you what, just for you, I'll try to make a test question that's got a Gaussian cone. I actually think, joking aside, I think that's a place we'd actually need Calc 3. Because the calculating volumes of cones is just, that's a piece of cake in Calc 3, but it's a...
So that's not going to be on the test.
Well, unless you think of a sphere as a kind of degenerate case of a cone.
I'm going to assume it's not.
So, but only a silly person would say such a thing. So, how about, what do you guys think?
A cylinder?
Cylinder. Mm-hmm. So a cylinder outside it or inside it, but the cylinder should be centered on the axis of the Gaussian cylinder should be centered on the axis of the, so we basically think about it being like here, right? Something like this, it keeps going and going, right? But for the sake of specificity, we usually draw a finite one. So we'll think about this Gaussian cylinder having length L and radius, little r, right? So the flux through this Gaussian cylinder should be, let's see here. So that the caps don't matter, right? There's no electric field lines cutting through the ends. All right. So all of the field lines are cutting through the curved part, which the area of that is what? It's 2 pi r times L, right? That's the area of the curved part of the cylinder. I usually call it the side of the cylinder. And that times E gives me my flux. The reason I can just multiply by E again is because the electric field is perpendicular. Yeah?
If it wasn't perpendicular, would you have to multiply it by like E cosine something?
Yeah, if I was so fortunate to have an example like that where I had a Gaussian surface where the electric field somehow had like a uniform angle over the whole thing, then I could do that. But I do not know of such an example. But I could try to create one. It's an interesting question. Don't worry, I don't have that much time this weekend. So, so 2 pi r L E, but yeah, that usually comes up with more sort of like, just more standalone, not really Gauss law problems. Those kind of problems tend to be the ones where we give you the electric field, we give you a shape, and we ask what's the flux through it. There, you got to figure out the angle and pick the part. We did one of those last week, I think. But so then the question is, what's the charge enclosed, right? That's the trickier part, isn't it? See, because I need to figure out what's the charge enclosed there. And so to figure that out, I'm going to go back to my picture over here. But first I'm going to clean it up because those field lines are in the way. So if this is the, it helps to look at the cylinder sort of two-dimensionally sometimes, for me at least. So looking at it dead on, my Gaussian cylinder looks like this, right? And let's see here. So it's going out to R. And so it's helpful for me to invent yet another letter, because I'm going to have to do an integration, you see, because the charge density, this is dq dv, right? The charge per unit volume, dq dv. It varies with R. So the way I want to do it is to chop it up into cylindrical shells, like we did Calc 2, remember cylindrical shells? Like that. And I've already got big R has been used and little r has been used, so we're going to go on to S, okay? So think about a cylindrical shell at radius S here. Sometimes that's half the battle, just coming up with a letter to express what you're doing, right? Let me not use this evil green marker, which is invisible to the camera. So what I'm doing here is I'm thinking about, I want to think about a shell, right? On that shell there's dq, you see? So this is a cylindrical shell. It's at radius s from the center of the cylinder, and the thickness of this guy is ds, right? So I want to figure out what's the formula for that. What's the dq here? It should be rho dv, right? Now we know what rho is. It's up there. I'm not going to write it down until we figure this out a little bit better. But what's dV? So, you know, we're talking about this slice in here, right? It's just a little slice. So I have rho. To get dV, I can do L times dA, right? A little bit of area from that annulus, right? What's dA? ds is part of it, for sure. How about 2 pi s ds, right? So if you can imagine taking the purple thing and just laying it out flat, right? The thickness would be ds, and the length of it would be the circumference of the strip. Does that make sense? Or? So, okay, then what? Well, this is true for what? For 0 less than or equal to s less than or equal to r, right? And so to find the charge enclosed, we're going to do the integral from 0 to little r, right? Because I'm sorry, my bad. The purple thing, we don't go all the way out to big R, right? We go to where? Just the Gaussian cylinder, right? Which is the blue thing. So this just goes to little r, right? Do you guys see it? Would you see what that is? Because we're trying to figure out the electric field at the little r, which is not all the way out to the edge. All right. So Q enclosed, it should be. I'm going to keep the 2 pi L out front. Then my S, 2 pi L S, and then rho. Now, what rho of what? What's that formula look like here? To be clear, this should be rho what? This is rho at R equals to S, right? If you like, I mean, it's at S. Maybe I should just say at S because, this is one of those places where it's like, maybe you've experienced this graphing where you're using X as a variable and also as a specific point on the graph and you get like, what can I say? Because the X is a variable, but the X is the point I'm thinking about. This is what we're up against. Anyway, let me write down the formula, then all will be clear. Maybe. So alpha times 1 minus S over R, big R. Yeah, ds. Now this integration is not too bad. We can pull a lot of this stuff out. We got a 2 pi L alpha integral from 0 to R of apparently S minus S squared over R ds, which gives us a 2 pi L alpha S squared over 2 minus S cubed over 3R. Evaluate that thing from 0 to little r. So lo and behold, we got ourselves a 2 pi L alpha little r squared over 2 minus little r cubed over 3r. There's my charge enclosed. Yay. So let's put it all together. We have 2 pi r L E is equal to Q enclosed over epsilon naught, which in this case is 2 pi L alpha divided by epsilon naught times r squared over 2 minus, if you guys see me make a mistake, like don't wait, like just jump in. And if you're wrong and it's not a mistake, you slowed me down, not a problem. And if I did make a mistake, you saved 5 minutes of your time. So if you see something, say something. You know? Now, fortunately, this is an odd problem, so we can check my answer. So we're not, you know, we're not without a friend in the book. So then, what do we got here? Notice what happens. The L should cancel, right? That was an arbitrary made-up length we did for the Gaussian cylinder. So that L cancels. What do we got? The 2 pi cancels too, right? So this cancels with this and this, and we just get E.
I do have a question.
Uh-huh.
Down there, after you integrate, you got r squared over 2 minus r cubed over 3r.
Yeah.
But up there, you just have the r squared over 2 minus r cubed over 3.
Oh, thank you. Very good. Yep. There's got to be an r down here, otherwise it's dimensionally inconsistent, right? We can't have a square of a distance plus a cube of a distance, unless we're just omitting units in the problem, but we're not doing that here. So, thank you. So we divide by r then, right? Basically, what it boils down to just divide by little r, and you got yourself a alpha over epsilon naught, right? Times 1/2 r minus 1 over 3r r squared, I think. Okay, well there it is. Does this make sense, like physically? And this, of course, is just for 0 less than or equal to r less than or equal to big R, right?
Why do you actually not?
Okay, so what's the total charge enclosed in this length? Like, what if instead of we made the Gaussian cylinder like bigger, right? What if we did it like out here, right? The other case like that. Then what would charge enclosed be? It's the same calculation, right? But the integration goes from 0 up to what? Yeah, 0 to the big R, right? Because you get the whole charge. And so that is whatever this works out to if you plug in big R, right? So you get 2 pi alpha times L big R squared over 2 minus big R cubed over 3R. And so then the electric field in that case, and of course that's you know, sorry, 2 pi R L E is equal to Q enclosed over epsilon naught. What's that give us in this case? This is that, you know, so we get basically the same algebra again. I guess we could simplify this a bit. What's this?
2/6. Oh, yeah, 2/6 r squared. Or 1/2.
Oh, okay, so this is a half minus a third is a sixth, but then you got the 2, so it's 2/6. But 2/6 is a third, right? So you told me a third overall, right? So it's pi alpha L r squared over, what did I say, 6? I think. If you multiply the 2 through, you get 1 minus 2/3, which is a third. Yeah, you said a third, didn't you? Sorry, I'll get it eventually. So if we set that, let me just do the algebra down here. Sorry, I'm starting to think about skipping steps, but no good will come of that for today. And so what does this give me? E equal to the L and the pi, they'd be canceling. We got, goodness gracious, my eyes. Alpha r squared divided by 6 epsilon naught. I said it, but let me write it. I need to see it for myself at the moment. L cancels and the pi cancels. That just leaves me division by 2 in the r. So I get little r, like that. You can compare this to like the other formula we've seen before, which is lambda over 2 pi epsilon naught times 1 over r. That's like the usual formula we get for a line charge. And so you could kind of compare these and figure out how much charge per unit length you had by comparing these if you felt like it. And my point is it's the same dependence. It's what I'd expect. It's reciprocal with the distance from the cylinder. And like this is basically like whatever number it is times the 1 over r, that's a constant. That's the characteristic of how much charge there is. It's wrapped up in the choice of alpha here and also r, big R. But I guess, okay, so the question is, this is just kind of a side comment. Do these match up? The problem asked us, do these match up when r equals to, little r equals to big R? Does it work? Oh, goodness gracious. I think the answer is yep, because a half minus a third is a sixth. So, and the r's cancel. Should I check the answer in the back of the book? It's right? Okay, woohoo. All right, which one do you guys want me to do next? I'll try to keep it moving here. Go for it.
So, I know like we had to do the integral on this, but there's sometimes we don't have to use the integral at all. I feel like they're kind of similar to these.
Mm-hmm.
Like, do you have an example that would be
Where I wouldn't have to do the integration?
right?
So I don't need to do the integration when the charge density is like uniform. If the charge density is uniform, then we end up not needing to do an integration. But if the charge density is not uniform, then pretty much we're going to have to do an integration to figure out the charge enclosed. That's pretty much the difference.
So since the density is like it changes.
Right, since here, yeah, exactly, since the density in problem 49 varied with R.
So like if rho just equal a constant, or they just didn't use the rho, they just had like Q enclosed, it would just be fine.
Yeah, I think more often than not, when we have a uniform density, we just got to tell you guys, like, you got to charge Q over the whole thing, and we just kind of like, you know, leave it to you, I suppose. If you want, I can break from the textbook for a second and show you an example which, you know, doesn't involve integration, but involves a density. Like, for example, start with a sphere, radius r, charge q, uniformly distributed. All right. Then chop out, cut out the half of, like the middle half of it, okay? Like cut it out to radius half. So take this and just cut out like the inside. All right. So this is, I don't know, I don't know how to draw, how do you draw a gumball that's not opened up, you know? I mean, that's I'm trying to say this is a hole, okay? So like, I'll draw sort of this is R over 2, hole. But out here, we still have the same charge distribution, same density we had before, all right? Then the question is, what's the electric field in all of the different cases? There's 3 cases to think about. Inside the hole, inside the charged region, outside the charged region. So I don't think I need integration for this one. Yeah.
Is this any different from just
Pretty much. So like, I mean, so like here's the three cases. I'll draw three pictures. So I got this one, this one, this one. So here's my whole. I'll draw it two-dimensionally so it's easier for us, yeah? So to start with, if I put my Gaussian sphere in here, I get my flux equals to charge enclosed over epsilon naught, and then what, you know? So this would be like R less than R over 2, yeah? So this is 0. So therefore the electric field is 0 because the electric field has got to be symmetric because everything else is symmetric. So the field would have to be radially outward or inward. And that's your only choice by the symmetry here. Therefore the electric field inside is 0. All right. Now, on the other hand, here's the interesting, well, let me do the uninteresting case here, like this. You know, if we're out here at radius r for the Gaussian sphere. So r greater than r, then the electric flux is 4 pi r squared times the electric field, and that's equal to Q enclosed over epsilon naught. Now, I guess the question then becomes, wait a minute, what is the charge that's enclosed? Because we got rid of some of it. Because we cut out, you know, that hole, and we cut out the charge with it. That's the idea. Okay? So how much charge is on the cutout sphere? Can you guys tell me? How would you figure it out? Ratio, yeah, ratio, right. So what ratio would you do? Ratio of the volumes, right. What's the volume of the holy sphere? It's what? It's 4/3 pi big R cubed minus 4/3 pi R over 2 cubed. So it's the total volume minus the part that you cut out. That's how to figure out the volume of a shell like that. Just like a, you know, for like a annulus, for between two circles, you calculate the area by subtracting the area of the middle piece out from the, you know, just like that. And downstairs, well, 4/3 pi r cubed would be the total volume, right? If I'm setting up this fraction, right? This is the fraction of the remaining volume to the total volume, right? So I just multiply that by Q, and that should give me the charge. So it looks like I have subtracted an eighth. So I think if I've done my math right here, I think that's 7/8 Q, is it? For the 4 pi over the r cubed and the 4/3 pi, those cancel, right? So you just can focus on 1 minus 1/2 squared, which is 1 minus an eighth, which is 7/8. Which is kind of disturbing, right? But remember, we're talking about volume here, and if you half the radius, you don't half the volume. It's not like that, right? Like doubling the radius doesn't just double the volume, it makes it 8 times as big. So this makes sense. So 7/8 Q is what we got over here. So the electric field outside this contraption is 7/8 times Q divided by 4 pi epsilon naught times 1 over r squared, right? So I'm writing it this way to emphasize it's the Coulomb field for the net charge in the shell, right? That's what's going on here. And the middle case is the kind of, well, I don't know if it's more interesting or not, but how about this one? What would you do here? You need to figure out what the charge enclosed is again in that case, right? If we've got r over 2 less than or equal to R, less than or equal to R. In that case, we need the charge enclosed is what? It's whatever, what's the volume? What's this volume here? I mean, we do the same thing we just did, right? We do 4/3, so we're at radius R, right? So we do 4/3 pi R cubed minus 4/3 pi R over 2 cubed, right? This here is R over 2, right? By assumption. So the difference of the Gaussian sphere's edge, the ball that bounds, and the ball we cut out, which is at radius R over 2, that's the volume of that shell. And of course I divide by the total volume, which is 4/3 pi R cubed. That gives me the charge, that gives me the density. Excuse me, that doesn't give me the density. That gives me the ratio of the total volume which the shell takes on. We take that ratio times the total charge. That gives us the charge in the volume. So total charge is given to be Q. And so this time it's a little bit more complicated, but we can cancel like the 4 pi over 3, right? And so we just get like R cubed minus R to the big R cubed over 8, right? Divided by big R cubed, I suppose, times Q, right? That's the formula for it. And then again, the math here is the same pretty much. We've got the flux is 4 pi R squared E, which is equal to, R cubed minus big R cubed over 8 divided by big R cubed times Q. That's all divided by epsilon naught, right? This is Gauss's law. And then solve for E. What do you get? You're like, a headache? Yeah, that's what I'm working on. Let's see here. So I've got myself a Q over 4 pi epsilon naught. I just decided to keep that out front. And then I'll bring my R squared down here too. And then I've still got R cubed minus big R cubed divided by 8, all divided by R cubed. So I think that's it. The idea I'm using, you need for one of the mission problems, right? Like there's a shell problem in the mission that involves this kind of calculations. Does that, and we can always check our answer, does that match? What should happen? When we put little r equal to what? Equal to big R, we should match that third case, right? Because there's no localization of charge at the shell, like it should just continuously patch together. Does it? If I put little r equal to big R, I get 1 minus 1/8 is 7/8. And then I also get the R cubes cancel, so I just get a factor of 7/8 here. So I get 7/8 Q divided by 4 pi epsilon naught R squared. Hey, that's it, yeah. I should have signed this one in the book. Is this one in the book? I don't know, it should be in the book. There's problems like this in the book. There's definitely a problem like this in the mission, so. Anyway, what would you guys like me to work next? Or you got a question? Or?
If it wasn't a hole, would it just be kind of serving as a point and the proportion would be 1? So it would just be field equaling K Q over R squared.
Yeah, if there wasn't a hole, you're right, it would be Q over 4 pi epsilon naught in case 3. And in case 2, we'd be back to the in-class example we did of the uniformly charged sphere. Yeah. Yeah. And then, of course, there's other variations on this theme. Like, it's fun to take this example and then just throw like another charge, boop, in the origin. And then you just get the Coulomb field of that charge out to the shell, and then that just kind of adds to all these cases by like essentially superposition, you could think of it. But you don't need superposition here. If I put a charge at the origin, I can still just do Gaussian shells at each time. I don't need the like separation of methods like I did in class today. But superposition is always an option. It may not be a necessary option, like depending on the symmetries involved. So. Do 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 do. All right. Try to burn through some of these easier problems. 21, chapter 21, problem number, let's see here. You guys have to help me out. I don't want to rework a problem I've already worked in here. So if I start working a problem I've already worked, you guys will tell me, okay? I said I did 13, 21, 79. Wait a minute. I just did 13, 79, and 57 the first week, I guess. So I did 21 in class today. I did 23 in class today, sort of. I'm moving past it. So let's do 31. That's the next one. All right, let's try it out. 21, 31. Let's see if we can do that one. It has 2 blue dots. This may take us a second, right? It's not a 3-dot problem though. 3 dots, that could be trouble, right? So here we have a uniform line of charge with length 20 centimeters is along the x-axis with its midpoint at x equal to 0. Zoop, zoop, x equals to 0. And its charge per unit length, I call that lambda, is 4.8 nanocoulombs per meter. Probably should move the camera here before I get too much further. All right. Oh, a small sphere with charge minus 2 microcoulombs is located at x equals to 0, y equals to 5 centimeters. What are the magnitude and direction of the force that the charged sphere exerts on the line of charge? Ooh, I'm going to have to think about this. First I gotta draw a picture though, all right? So we've got this line of charge, right? They put it on the x-axis with its origin in the middle. I'll draw it like this just to make it bigger. And so it was 20 centimeters, so like this is 10 centimeters this way, and over here is minus 10 centimeters, truth be told, right? For x equals to 10, x equals to minus 10 by process of like coordinates, right? And small sphere with minus 2 microcoulombs is at x equal to 0, y equal to 5. Oh, so that's like right here. I regret drawing this so high in the board. I'm going to fix it. So here we've got x equals to 10 centimeters. Over here we've got x equals to minus 10 centimeters at the end, right? And we've got up here, that was supposed to be the midline. Oh well, my drawing is growing more and more degenerate as the day goes on. This is not right, but fine. So here, x equals to 0, y equals to 5 centimeters. We've got a charge of q equals to minus 2.00 microcoulombs. All right. The question is, what is the magnitude and direction of the force that the charged sphere exerts on the line of charge? Right? So, what do you guys think?
Would the line of charges be straight down?
Well, the line of charge is given to be horizontal.
Oh, wait. Yeah.
So that's a negative charge, right? So it's attractive because this is a positive charge per unit length, right? So it should be pulling it up, right? And it seems like it should be pulling it vertically because, right, it's pulling it, it's over here the force is going like that, the electric force is pulling like that. Over here the electric force is pulling like that. And by the symmetry, they're equal and opposite, they should cancel, right? So if I kind of draw that out, if I were to make a, kind of a messy picture, I would have like this, like this, like this. Oh, my bad. Because it's not there I should be drawing the arrows. What are we talking about? The force that this guy puts on that, right? So I should be saying we've got, this is my dF here. The dF here is easier. And then over here, that was supposed to be the same length as the other one. Oh, well, I tried. You get the idea. The point is that there is also, one here, and there's also one here, and those are also like paired, right? Not that they cancel out, just part of them cancels out, right? So the net force is vertical. So we see that the net force is equal to something like 0, Fy, right? And so we're going to have to figure that out by integration. What is dF here? So let me go back to basic principles, which is Coulomb's force, right? The Coulomb force law. And so the question is, I'll draw it down here. We've got the point up here at, I'm going to drop the units for a bit, 0.5, okay? And actually, I'm feeling slightly guilty about that. No, I'm going to get over it. Oh, fine. Fine. 0L there. I feel better. L equals to 5 centimeters. See how I do that? Now this is 2L. And this is minus 2L. And now I don't have to write centimeters, but I'm also not like violating unit conventions. Yay. So I feel a little bit better. Anyway, I'm trying to figure out what's the force down here on this point, which is at like x comma 0, right? And that's based on the distance, this distance right here, which we sometimes call like script r. And so if I look at this triangle, we should do that, right? This is what? This is x, and this is L. See, every time I write L, I save myself the trouble of writing 5 centimeters. It's worth it. It's a good trade. But, all right, so I'm interested in, so like the, of course, this is my dF, right? So, I mean, I can draw another picture over here, which has got dF, and it's got the two pieces like dfx and dfy over here, right? It's the same angle though. If this is theta, this is theta, So dfy is apparently what? Just for the magnitude, no vector, df. Sine theta, right? Very good. So it's sine theta times df, which in this case is, in terms of L and X and stuff, should be L over R, right? What is R? Square root of X squared plus L squared, right? So I'm up against L over the square root of X squared plus L squared. All right. What's my dF? That's the magnitude of the Coulomb force, right? Remember, dF here is equal to K dQ big Q, times little q divided by script r squared. That's k q1 q2 over r squared. Now dq is what I have in mind as the little itty bitty charge right here, whereas I've got lowercase q up there. But dq is also found up here. See, this is dq dx, yeah? So that tells me that my dq is actually lambda dx, where lambda is that particular constant. So this is in fact k big Q lambda dx over, you know, little r squared, which we could write as x squared plus L squared, yeah? Put this all together, and we got ourselves a dfy of k q L lambda dx over x squared plus L squared to the power 3/2. I think. What do you guys think? So then what?
Do you not just integrate from there?
Mm-hmm. Right, and then, but what do we integrate over? So then we have to calculate, you know, the net force. I'll put it up here. Maybe I can fit it here. F y equal to, let me take all that constants out. So we got a k q L lambda, right? K q L lambda. Oh man, this. Oh well. I tried. See, that's all that matters, right? Let's see your k q L lambda integral, and the integral is from minus L to L, right? Of dx.
Is it
X squared.
2L to 2L?
You're probably right. Is it minus 2L to L? It's a good question. Minus 2L to L, 2L. Totally on board with you. So you take my integral, raises me at twice the integral from 0. I like it a lot. That makes sense. It's an even function. Yep. Well, but we just needed sine theta to pick off the vertical component. We were looking for the y component, so we multiplied the magnitude by sine theta. So that sine theta doesn't have a theta. I mean, the sine theta we can write geometrically as the ratio of the opposite side to the hypotenuse. Yeah, yeah. And then we just got to integrate this thing. So I believe this is a trig substitution. And we let x equal to, I want to say L, maybe I feel like a secant theta might be the way to go here. L secant theta maybe? Then x squared plus L squared equals to L squared secant squared theta plus 1, also known as, remember secant squared theta is equal to 1 plus tangent theta squared theta, right? Which suggests I have made the wrong substitution. Yes, sir? So that was not a secant theta problem. This is a tangent theta problem. This is why I need to teach calculus 2. Again, it's starting to fade. Oh well. But I checked my work, so we're okay. So anyway, tangent theta, that's better. Tangent squared theta plus 1 is secant squared. And lo and behold, dx is L secant squared theta d theta. Now, if we want to change the, I don't really want to change the bounds. I'm gonna leave myself room here. 2 k q L lambda. I'm going to put the thing I find down here eventually. Oh, you know what? No, let me just, I'm sorry, I'm being lazy. Let me think. Yeah, exactly. So, all right. So the point here, the point here is that if x equals to L, if x equals to 0, that implies theta is equal to 0. Okay. And if x is equal to 2L, that tells me that 2L is equal to L tangent theta, which tells me that tangent theta is equal to 2. So I can do inverse tangent of 2, I suppose. Although it may be more convenient for us to, when we actually get into the details, to come back to that more directly. All right, so I'm sorry, I feel like I have to erase the dfy now, can I? Okay, good. So, all right, so we've got 2kql lambda, integral from 0 to inverse tangent of 2. I'm going to call that theta 1. Integral from 0 to theta 1. My dx was L secant squared theta d theta, and I've got, x squared plus L squared, which was L squared secant squared theta. So I've got myself an L secant theta quantity squared, all to the 3/2 power. Huh. Hey, that's 1 over secant theta. Oh, this is nice. So we've got 2kq lambda little l squared integral from 0 to theta 1 cosine theta d theta, which gives us 2kq lambda l squared sine theta 1. And we can do better if we just go back to, like, this is sine theta 1 equal to 2. I mean, tangent theta 1 equal to 2. Yeah. It's like, here's theta 1. So if that's theta 1 and tangent theta is equal to 2, that's the ratio of sine over cosine, right? So if I put a 1 down here, then that puts it 2 over here, right? That's the tangent theta equal to 2 triangle. And as such, this over here is the square root of 5, which makes the sine of this angle 2 over root 5. So we've got 4k q lambda L squared divided by square root of 5. And then I guess I could put in the stuff, right? Fine. So that's 4 times 9 times 10 to, oh my goodness, I've forgotten what k is. This is bad. 9 times 10 to the 9th, right? And then my lambda was 4.80 times 10 to the minus 9th. Oh, those cancel. That's nice. And my L squared is 0.1 squared divided by square root of 5. And the units on this had better be newtons. My energy is starting to get low. Let's see here, 4 times 9 times 4.8 times 0.1 squared divided by square root of 5. This is giving me 0.772. 0.772 0.28 newtons. If I haven't made a mistake, please let me not have made a mistake.
What's the correct number for L? Is it 5?
Ah, thank you. Yes, L was 5 centimeters. Thank you. You have saved me from disgrace. Let's see here. I usually make a mistake right at the end. That's my custom. Oh, I shouldn't have erased that. So I should just take what I did, and I think, oh, I'll take what I did, I'll multiply it. No, I'll divide it by 0.1 squared. That undoes it. And then I'm going to multiply it by 0.05 squared to be safe. I get 0.0, I mean 0.193, 1932, 0.1932 newtons. Is that it?
I have a quick question.
Oh.
It's more like a concept. It's not like taking it to work. So you're showing like planes of charge in class, and then like the field lines, right? Like the electric field lines.
Which number was this? I'm sorry, you gotta give me a second. I can't, I have to get this behind me. What problem was this?
It says 3.09 times 10 to the negative 3.
Which one was this? Number what?
2131.
2131. 3.09 times 10 to the minus 3 in the positive y direction. 3.09. Ah, I've made a mistake somewhere. Anyway, your question though.
Yeah. So like two sheets, they both have uniform charge across both sheets,
Mm-hmm.
and they're just laid out parallel, right?
Yeah.
In my mind, I think the charges just repel, right? And the field lines would just be in opposite directions. But then when you work it, since it's infinite, they go both ways. Is that the
Well,
case?
it's always, so like any, if we have a conducting, not a conducting, if we have an insulating, if you have a sheet of charge, right? So that means the electric field lines can go on both sides of it. Half of them go this way, half of them go that way, but they go away from the charge, above or below. So when you have two planes, when you have two planes of charge, it's the same thing for both. It's just the top one, the electric field goes up, and the electric field goes down. For the bottom one, the electric field goes up, and the electric fields go down. It's just in between, you've got up and down, and they balanced out to zero,
Okay, so it's like,
if they're equal charge.
oh, because the opposite lines are going towards the other sheet.
Right.
Yeah, that makes sense.
The different one was if, so I'm sorry, I don't know what who knows what
At this point, it's too far gone to.
but it's something stupid, like, this is the method to solve this problem though, all right? Like, so I probably like, oh, by the way, like you do not have to give your answer in terms of exact radicals. Like that's not part of this course. I'm just being a Calculus 2 instructor for a second there. Like it's totally legit to use, you know, sine of inverse tangent of 2 and whatever decimal that gives your calculator. Like in fact, I'd prefer a decimal answer for physics. I don't want answers in terms of the square root of 17 or something. What is it? Yeah. Let's see here.
So this is chapter 21.
Yeah, this is chapter 21. I was trying to work a decent problem here. Is there any other problem you guys like me to work? Like,
Just look at this mission.
how about number 38 and 21? We haven't worked that for a while.
Probably gonna send it or something at 5:30.
That's fine. Yeah, well, you better go.
Yeah.
Yeah, if you guys have to go, we can stop here. That's fine. You done? We're done?
I'll watch another one. I'm good. Do that one.
Do another one? All right.
You're up for it, yeah.
I'm up for it.